Well, thanks everybody for joining. And let me repeat the plug that Terry gave, which is anyone interested in doing a DandBites, please just raise your hand. The topics can be broad. It doesn't have to be things that we're using immediately. The point is to share things that we're working on, thinking about, and learning. And this talk is it's something that it is a math talk, so don't expect to see a lot of code, and it's not even things that we're going to immediately use here. But I was motivated to prepare something when I learned of the death of Ron Graham, who was a real giant of math and computer science, who died at the beginning of July. And so Ron was a very, very interesting person and a really broad contributor. He inspired a lot of us who, I myself as a mathematician was somewhat of an oddball in that I worked in a bunch of different areas. And in today's world, that's actually fairly rare. There's a lot of the kind of natural social pressure in academia is to develop a narrow specialty and really contribute in that area. And if you look at the giants of the past, the Gausses and the Eulers and the Riemanns, you don't find mathematicians like them much anymore. But Ron Graham was an example of one who was like that, who was a real mathematical polyglot. He was also a circus performer in early life, and see an example of his juggling mastery. He was for a while he was, I think, the president of the International Jugglers Association. There are those who claim that the picture here has been doctored, but you never know. It's Ron. And he said he learned from the circus, from performing in the circus, he learned one very important thing, which is you want to do things that look hard but are easy, not things that look easy but are hard. I've always thought that was a really good piece of advice. He was also another one of the great mathematicians of our current time is Paul Erdős, who's still alive. He's also a polyglot, somebody who contributed to lots and lots of different areas, and he contributed to so many different parts of math that we invented this concept called the Erdős number, which is the length of a path in the graph that connects you to Paul Erdős if you're a mathematician, and edges on the graph happen when you've written a paper with somebody. So, for example, my Erdős number was 2 because my thesis advisor, I wrote a paper with my thesis advisor, and he wrote a paper with Paul Erdős. And Ron Graham, people used to kid and say his Erdős number was 0. But in any case, this is just, I did want to say some things about Ron because this is what kind of inspired me to do this talk. And hopefully if, you get anything out of it, it's a sort of fascination with some of these basic questions that Ron thought about. He contributed to all the areas that I've listed here. And one area is this area called Ramsey Theory, which is really a kind of a fascinating area within graph theory and combinatorics that does have a lot of applications to networks. I'm just going to very briefly touch on a couple of them, but it is an area that is very sort of tantalizingly simple, but very hard when you actually get into it. Okay, so I'm going to start with a motivational example of, get you thinking a little bit in the way of Ramsey theory. So suppose we have a party that 6 people go to. 6 people, and the question is, who knows one another? A lot of parties, nobody knows anybody. There's other parties where everybody knows each other. A sort of interesting statement is that we can actually prove that no matter how you do it, no matter what group of 6 people you select, you've got to have at least 3 people who know each other, they're all mutually acquainted, or 3 people that just are totally unacquainted. So the 3 that know each other, we'll call it clique, and the 3 that people that don't know one another, are what we call an independent set. And a lot of Ramsey theory comes down to, how big does the group have to be in order for these kinds of statements to be true. So, okay, I made the statement, and I'm actually now going to walk us through a really simple proof of that statement. So here, imagine are the people, and apologize for the lack of diversity in the faces, but at least they are wearing masks. And what we're going to do is we're going to draw blue lines between people who know each other, and red lines from among people that aren't connected. So the cliques are going to be the people that are designated by blue lines, and the independent sets are what we'll show in the red lines. Okay, and so what the statement I made before comes down to is, show that it's impossible that not to have a triangle in one of the colors. When you think about it, 3 that all know each other, they're going to make a triangle that's blue, and 3 that don't know each other are going to make a triangle that's red. So it really comes down to, can you draw connections, among all these, because they either know each other or they don't. Can you draw arrows between all of these people in such a way that, and you only have 2 colors to work with, blue and red, and can you do it in such a way that there aren't any triangles? And the answer is no, you can't. And I'm going to show you, sort of walk you through an argument to demonstrate why. So start with one person. Okay, now this one person either has to have 3 blues coming out of him or her, or it has to have 3 reds. Why is that? Anyone can just pipe in here. Why do you have to have 3 of one kind? You have to, I guess, do *7 to unmute yourself. Don't be bashful. It's pretty simple.
Could it be because there's the same probability that they know someone that they don't?
Well, that's an interesting probabilistic statement. We didn't assume that, but this is just really sort of basic arithmetic in a sense, because out of this person, there's either remember there's either a blue or a red that goes to every single other person. So the arrows coming out.
Maybe because somebody invited him, and then for it to be a party, somebody.
Oh, that's right. Okay. You
invited somebody else.
You're thinking too much. You're putting too much thought into this.
So Phil, there's five people that he could that are other than him at the party. He has to be connected to each one in one way or the other. So he there's no way to not have 3 just because of that.
Right, exactly. This is why that's very good, Ralph. This is like really like I said, it's simple. So it has to, and this is the kind of argument that we end up all the time in Ramsey theory, because it's sort of bin packing. There's got to be 5 arrows coming out of this person's head, and so that means you're going to have 2 and 3. So at least one of them got to be 3. Okay, so let's assume that the 3 is the blue. Okay, fine. Now let's continue to play the game. Now look at these 2 other people that now I've circled here, and think about what's between them. Well, if I want to keep playing the game of not getting a triangle, I've got to make the edge between them red, because otherwise I end up with a triangle. So it's got to be red. Fine. Okay, now look at these other 2 people. Again, if I want to keep playing the game, I've got to make that edge red, because otherwise I make a blue triangle. Okay, so now at this point, when we look at the bottom two, we're kind of hosed. There's no play left. If I make the edge between them red, then I get a red triangle with the guy on the upper right. And if I make it blue, then I get a blue triangle with a guy on the left. So this is actually a proof. This is, if you walk it through, if you think through the assumptions that were made along the way, it actually does prove that there's no way that you can do it without getting a triangle. Okay, so that's interesting. I'm now going to just have a really quick, I told you there wasn't much math assumed here, and there isn't. This is really basic. I just want to review a couple of quick things. Binomial coefficients are these numbers that we say n choose k. It's the number of ways to choose k elements from a set with n elements. So, for example, 4 choose 2 is 6. If you start with a set with 4 things that I've shown over here, 0, 1, 2, 3, I actually listed out all the 6 subsets you could make. Okay, these things turn out to be tremendously useful in combinatorics. That we very often have situations where what we need to count is the number of ways that you can choose a subset of a larger set. They're called binomial coefficients because they're also the coefficients that you get when you expand the binomial expression a plus b to the n. So like a plus b squared is a plus 2ab plus b squared, and if a plus b cubed is a plus 3ab squared plus 3b squared a plus b cubed. So you can get the coefficients of binomial expansions by just looking at these numbers. This is actually a deep fact that you learn in elementary algebra called the binomial theorem. They satisfy a recurrence relation. You heard me spout off a couple of them, actually using in my head the recurrence relation that we just talked about. The Pascal's triangle is this picture down on the bottom that you saw. I said a squared plus 2ab plus b squared, and a squared plus 3ab squared, and so on for the cubes, and then you get down to the fourth. And what's really cool about it is that to walk down the triangle, you just add the elements that are adjacent above on each row. So the 3 in 1, 3, 3, 1 comes from adding the 1 and the 2. And that is from this recurrence relation that n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. To see why that's true, one way to see it's true is to think about choosing, if I want to choose k things from a set with n elements, I can say, okay, let's play a game and let's pull one of them off to the side. And then I can look at, with that one excluded, to get a k element set, I now have n minus 1 choose k. That's the ones that don't include my special designated element. We'll call him Bob. But then I obviously haven't counted all of them. Now let me count the ones that do include Bob. Notice they're completely separate from the ones that don't include Bob. So I get to add. It's plus. There's no intersection. So the ones that do include Bob, well, what do I really have there? Now I have n minus 1 other elements, not Bob, because he's already chosen, he's already won to get in there, and then I'm choosing k minus 1. So that's the kind of theoretical. We can prove that all these things in multiple different ways, but this is a fundamental fact about binomial coefficients, that they have this recurrence relation. And we're going to use that in the proof of Ramsey's theorem. Okay, Ramsey's theorem says that, first of all, the Ramsey numbers are simply defined and devilishly hard to compute. So RST is the smallest number n, such that any graph on n vertices has to contain either an independent set of size S or a clique of size T. And what we actually saw in the motivational example was that R33 is less than or equal to 6. Why do I have to say less than or equal to 6? Well, the answer is that I looked at 6. I know that it can't be bigger than 6, because if I start with 6, I know I have to have either an independent set of size S or a clique of size T. That's what we proved. We proved that if I start with 6, there's no avoiding getting an independent set of size 3 or a clique of size 3. That's what we showed. But we didn't show that if you start with 5, you don't have the same thing. That if I start with 5, can I do it with 5? And what I'd like you to do now is just think in your head. Suppose there are 5, and play the same game with 5, and tell me, can you think of an example where you don't have an independent set of size 3 or a clique of size 3 on a graph with 5 things in it? So I won't ask you to draw because we can't all see it, but I think you can probably do it in your head. You can come up with examples. So that's just another, some fun thing, little thing to do, is to see that if you used 5, you actually could get your the Ramsey number for 3 and 3 isn't 5. It has to be at least 6. So that's what the way the Ramsey number is defined is it's the smallest one that forces you always to have at least that many that are independent, or a clique of at least that size. That's the definition of the Ramsey number. Okay, and the answer to my question here is yes, R33 actually is 6. Okay, so what Ramsey's theorem says is that, first of all the Ramsey numbers are finite, and it produces a bound for it. It says that RST is less than or equal to S plus T minus 2, choose S minus 1. So that's actually an upper bound for the Ramsey number. So what does that mean? It means any time that you have a graph that has at least S plus T minus 2, choose S minus 1 vertices, you are going to either have an independent set of size S or a clique of size T. Often Ramsey's theorem is interpreted to say something like complete disorder is not possible. You have to have regularity that's emerging as you in a set of any, once you get to a certain size, patterns have to emerge. And we'll see some examples of why this is relevant, why it's interesting, kind of what value it has. All right, I am going to go through a proof that really is a sketch of a proof, and there's some things that are left out, and that'll be fun for you to work on, assuming you're sufficiently motivated to actually look at them, like the last little exercise that I gave. Okay, so the way we're going to do this is by mathematical induction, and it's a little bit tricky because it's actually simultaneous induction in both R and S, which means we sort of build up the result by showing that it holds for R1n for any n, and Rn1 for any n, and then build it up from there. Let me stop and ask, why is it obvious that the base case in both of those cases holds? So remember, Rn1 says that you've got Rn1 has got to be, what do we know about the, can you tell me just immediately what the value of Rn1 is for any n?
Is it 1?
Yeah, it has to be 1. And that's because, and why is it 1?
There's always an independence guy. It was a T.
Yeah, you look at a set like a one element graph, it's independent. The whole thing is independent. So, and similarly, you can see it the other way. So, okay, so what we're going to show is we're going to, if we can show that this inequality on top holds, that RST is less than or equal to RS minus 1T plus RST minus 1, then we can use that recurrence relation that I showed you to you use the inductive hypothesis, you apply the inductive hypothesis to RS minus 1T and RST minus 1 to assume that they're less than or equal to the expression for S minus 1T or ST minus 1. And then you notice that those two expressions in the middle add to the expression on the bottom by the recurrence relation of binomials. So all we have to show is that RST is less than or equal to RS minus 1T plus RST minus 1. Okay, so how do you do that? Well, let's start. Imagine that we've got a graph that has the sum of those two numbers vertices. So what we need to what we need to show is that it's either got an independent set of size S or a clique of size T in it, because that will show that RST is less than or equal to that sum. So okay, so let's look at a vertex, pick any one of the vertices that are in that graph. Now, suppose that, first let's suppose that there are RST minus 1 other vertices connected to it. Okay, suppose that it's got RST minus 1 other vertices connected to it. Well, then what you want to do is consider the subgraph, G prime, that consists of all of the vertices in G that are connected to V, but not including V. So I claim that G prime has to contain an independent set of size S or a clique of size T minus 1. Why is that? Okay, the reason that has to be true is that, remember that G itself has RS minus 1T plus RST minus 1 total vertices. So it definitely has at least RST minus 1 vertices. And if you take one away, as long as RS minus 1T is at least 1, which we know it has to be, that means that it has to have enough vertices to have an independent set of size S or a clique of size T minus 1, because it has to be at least RST minus 1 big. Remember that the way that number is defined is that if you have that many vertices, you have to embed an independent set of size S or a clique of size T minus 1. So if that's the case, it has to have that. Now, in the second case, assume that assume that it has a a clique of size t minus 1. Assume if it has an independent set, assume that it has a clique of size t minus 1. Then we can extend the clique by adding v. So G then has to have an independent set of size S or a clique of size T, either way, because either you're adding it to the clique of size T minus 1, or it already has an independent set of size S. Okay, so now suppose, on the other hand, that there at least are S minus 1 T vertices not connected to V and G. We can then define G prime the same way, but including the vertices, instead you include the vertices that are not connected to V. And there you get the same result. You either have an independent set of size S minus 1 or a clique of size T. And the independent set can be extended by adding V. So therefore you end up at the top with at least a independent set of size S or a clique of size T. And you've basically proven the theorem. So this is, as I said, it's a sketch. It leaves out the base case, and it leaves out a little bit of the details of why you can actually add these things back. But this is the core of the proof of Ramsey's theorem. Okay, so now I want to talk, I have a commercial for LaTeX, which I wanted to give a commercial. If you want to make beautiful stuff like this, all you have to do is get LaTeX, and you can create it. But I want to now talk a little bit about some applications. So one application is in the design of networks. And this is the kind of stuff that Ron Graham worked on. And this is a very, very simplified example, but it does give you a little bit of the flavor of the kinds of things that Ramsey theory is applied to. Ramsey theory, broadly speaking, is the study of Ramsey numbers and regularities that happen in graphs, that happen in the layout of cliques and independent sets in labeled graphs. So imagine in the picture at the left that the nodes of a network, imagine these are all nodes that are connected by, that are part of a network. And imagine that the labels on the edges are the labels of intermediate facilities that sit between the nodes. So, for example, X1 and Z1 and X2 and Z2, and the X2 and Z1 are both connected via a single intermediary facility that's labeled R. So those are wires, you can say, go through that one transmission place. Okay, so if you take out that facility R that's labeled R, then you'll see that X1 and Z2, X2 and Z1, you don't have a path anymore. They are isolated. They're effectively cut off. So the interesting question to ask is, if there are just two intermediate facilities, as there are in this picture, the R's and the B's, what's the smallest network you can design so that it doesn't embed a graph like the X's and the Z's, so that if you take out a facility, you don't end up isolating a couple of nodes, a couple of pairs of nodes? And the answer to that question is you can do it with 5. So this is a challenge for the reader to actually draw how you could do it with 2 facilities and only 5 nodes, so that you don't embed a set of pairs that are similarly isolated when you take out a facility. So this is just a really simplified example, and it's just meant to give a little bit of the flavor of the kinds of combinatorial problems that people go after using Ramsey theory. Okay, here's another one, a confusion graph. Imagine that you've got, you're communicating across some kind of network with some kind of protocol, and we've got let's imagine ASCII only has the letters A, B, C, D, and E in it. And so your transmission alphabet has a set of letters in it. And the problem is that sometimes letters in a transmission alphabet can be confused with one another. That the transmission maybe has a little bit of noise on the channel, and you're likely to end up, say, interpreting a B as an A. But so the picture on the left would indicate that you might be likely to interpret a B as an A, but you wouldn't be likely to interpret a C as an A. So you don't have an edge between the A and the C because they are not likely to be confused with one another. So a confusion graph is a graph where edges indicate that things might be confused. And now what you tend to do in that type of scenario is you try to pick out an alphabet that you can use that is independent in the sense of that we described before in this graph. So like A and C together. If we just said, okay, fine, forget about B, E, and D, I'll just use A and C. If I can say everything I need with just those two, then there'll never be confusion, I'll be good. So the largest unambiguous code alphabet is the largest independent set that you can make in the confusion graph. And what people sometimes do is they will allow you to actually combine symbols to make strings, and then see, you can, like say AA and AC would not likely be confused, and that allows you to increase the size. Fun fact to know and tell for this graph, the largest independent set you can get is R33 minus 1, which is equal to 5. So again, the Ramsey numbers come into computing what is needed to build out transmission alphabets when you start with a confusion graph. And this is something that, again, basic telecommunications stuff that Ron Graham was a pioneer in. He spent a long time in it, a good bit of his career at Bell Labs. Okay, so, well, this is all well and good, but there's sort of a big problem with Ramsey numbers. And we proved that they're finite, which is great. We showed that R33 is 6, and that is sort of left to the reader to convince yourself that it can't be 5. But you can do it. When you think about it, you can show that it can't be 5 by looking at every single graph, and that's okay. And in a sense, what we did for showing R33 is 6, we really got into the structure of that complete graph on 6 vertices and showed something from it. That works for very, very small graphs, but it very quickly becomes very painful, but surprisingly. R44 we know is 18. The next fact is sort of stunning. When I first saw it, I said, "Are you kidding me? Why is it that R55 isn't even known? It's not even known. R55 just says, what's the smallest complete graph that any way that you color it in 2 colors, you've got to either have an independent set of size 5 or a clique of size 5. How hard can that be? And there's a famous quote from Paul Erdős that he says, "Suppose aliens invade the Earth, and they're going to, destroy us all if we don't tell them what R55 is." And he said we could marshal the world's best minds and fastest computers, and within a year we could probably calculate R55. And he said this in 1990. Notice that the statement that I just made is still true. In other words, we still won't know what R55 is. So even since 1990, no one has been able to actually do it. And then he says, if aliens demanded the number for 6 and 6, we'd have no choice but to launch a preemptive attack. In other words, it's hopeless. So the question is, why is it so hard? And let's think about R55. The conjectured value is that it's 43. That's what, there is a conjecture. And if you want to go and get a PhD in combinatorics and you can prove that it's 43, I don't know if it'd get you. It depends on how interesting the proof was. But if you were able to prove it, you might well get a thesis out of it. So the problem is that the one way you're never going to get it is by trying to do just brute force. And so to verify by brute force, we need to look at all the colorings of the complete graph on 43 vertices, and actually all the numbers below 43 too, because you want to show it was the smallest number. So you'd want to say, 43, 42, 41, 40, all the way down to, until you got to the point where you could sort of demonstrate it was not possible. So, okay, well, how many, just how many ways can you color a complete graph on 43 vertices? So does anybody have any idea about how you would compute that? You've got two colors, two colors. When I say all colorings, I mean colorings with two colors. All right, well, move back to our binomial coefficients. If you look at the graph, you look at all of the pairs of vertices in the graph. If it's got 43 vertices, then you really have 43 to choose two different pairs of vertices. So that's 903 of them. And the problem is that each of them could be colored two different ways, and each coloring, every edge, every selection of a color for a pair of the edges it creates a different overall coloring of the graph. So that really means that you've got 2 multiplied by itself 903 times numbers of ways that you can color those vertices in the graph. So that's really about 10 to the 272 different colorings that you're going to have to examine. And then what you have to examine when you've got the coloring is you got to say, does it have an independent set of size 5 or a clique of size 5? And you got to search until you find that. So that number is huge. And even imagine the problem with exponents is that, when you divide, you only get to subtract. So imagine you could do, I don't know, imagine you could do 10,000 of them in a millisecond. That's only like, 10 to the 6th or 10 to the 5th in a millisecond. And then you multiply by 1,000, fine, you're only now 10 to the 9th factor. That only gets you from 272 down to 263. So you're still, eons away of being able to actually do the computation. So this is difficult, and it is it's part of the, what is sort of stunning is the fact that we really don't know what these numbers are, but these numbers are very important in the design of systems. And so a lot of results have been developed that make assumptions, simplifying assumptions about the kinds of graphs, about the kinds of colorings that are going to be acceptable. And this whole field of Ramsey theory that is applied somewhat extensively in computer science makes use of those simplifying assumptions. But I just wanted to kind of, what I wanted to illustrate in this talk was that, first of all, the combinatorics and graph theory are fundamental to a lot of the things that we do in computer science and networks. And also that what math often will give you is we can prove that that numbers with certain characteristics have to exist, but they become very, very hard to compute. And so this is an active field of research in math. Okay, I do have some references at the end that are that cover a number of things that I talked about. And at this point, I'll just say, does anybody have any questions? The Ron Graham's book is a really nice book. It is a Dead Trees book, but it really develops the theory nicely. And you can also just look at any book on combinatorics. If you're interested in combinatorics, please, if you want references on combinatorics books, you can ping me and I'll send that stuff along. As you saw, the mathematical, the required mathematical background in combinatorics is very similar to number theory, in that it doesn't really require. It's sort of built from whole cloth, and you learn the results as you go. Is this a problem that requires more math to be solved, or quantum computing? That's a really good question. And as a mathematician, my hope is that it's a problem that simply will be handled mathematically. So people will, before the space aliens come and demand the answer, well, we will have fleshed out the theory and we'll know what these numbers are. Let's see. Quantum computing could help. It definitely could help in extending our capability to do more computations, but the number there is really kind of daunting. What are the questions?
So I don't know if you read this one, Phil, but it was, if we were to know R55, how would that impact like real life? Like what would be a problem that we have that, solving this could just like help us?
Yeah, what it would, in a sense, it's the conjecture has already led to some discoveries where if you say, suppose that R55 for sure is 43, we know it's 43, then what that means is that if we search for designs of systems that essentially require that we have graphs, that have the characteristic, we can start. We can know that we're going to need at least 43, and that actually does kind of put some constraints on the design of some systems. It's hard to fortunately, there's a whole lot of math in between the kind of final results that people use in designing physical systems. But the fact is, if we knew what these numbers were, we could sort of narrow the state space of some of the systems we're designing. Is this a known NP problem? Certainly well, when you say is it a known NP problem, the search problem of trying to by brute force solve the problem, that's definitely an NP complete problem. Is there a, you know, is there something that's say a polynomial time algorithm that could compute Ramsey numbers? We actually just don't know that. We don't know the answer to that. We know that certainly the search problem is NP. Okay, what else? All right, well, crank it up. Have some fun, and if you're you know, if you do develop an interest in graph theory and you start, or combinatorics, and you have questions, you want help getting started, definitely let me know. In memory of my I would say my friend, but I didn't actually know him personally, Ron Graham. It would be an honor to to help people study this area, which is full of interesting problems. It's like number theory in that it doesn't require a lot of machinery to get going. You learn binomial coefficients, you learn some basic stuff in graph theory, and then pretty quickly you're into some interesting material. Okay, well, thanks everybody.
Thanks, Phil.
Enjoy the rest of your day.